Hello everybody, I'm putting together a video going through the answers to the practice test for our test on Friday. Hopefully this answers any questions you might have, but in case they don't, Miss Oswald and Mr. Evans will be around after school. You can go find them in either HH234 or J230 and you can go ask them questions, or shoot me an email, or just come in early on Friday and come find me and I'll answer your questions then. Number 1. We're looking for the maximum mass that this sphere can have so that the block doesn't slide. So we're looking at an equilibrium problem. The block doesn't want to move. So you essentially have to draw two force diagrams, one for this knot in the rope and another for the block. So the block is a little simpler. We've got the normal force up, force of gravity down, which would be the same, force of tension to the right, and a force of friction to the left. Those two also have to be the same for the block not to be moving. This is our force of friction, normal, tension, gravity. For the knot in the rope, you've got force of gravity down, which is essentially what we're looking for. You've got the rope up and to the right that's at that 32 degrees at the top. You've got tension to the left that has to match the other tension because it's the same piece of rope creating that tension. We can continue the triangle here. And 32 degrees angles at the top. I'm just going to change that to a 58 degree angle down here. And our up force on that triangle needs to be the same as the down force for the ball. So we'll just go 3 tick marks for those. Now we can't really do any math right away with the right diagram, but with the left, we can figure out the force of gravity and the normal force, and then take our normal force times mu to get the force of friction. So being 5 kilograms, that means our force of gravity is 49 newtons. And if you multiply 49 times mu, that gives you the force of friction is roughly 23 newtons to the left, like 23.03. And so that's the same as the tensions. And that has to also be the same as the x component of our triangle over here. And so now that we know one side of the triangle and the angle, we can use cosine of 58 and this side of 23 here. Well, pardon me, not cosine. Tangent of 58 and to find the opposite side. That opposite side is 36.9 newtons. So our force of gravity is 36.9 newtons. If we divide that by 9.8, we get a mass of 3.76 kilograms. Number 2. A 75 kilogram man stands on a scale while accelerating upward in an elevator. If the scale reads 850 newtons, what's the magnitude of the acceleration of the elevator? So quick force diagram here, which you should be doing force diagrams for all these problems, but quick one here. You've got your force of gravity down. That would be 75 times 9.8, which is 735 newtons down. We've got 850 pointing up. So the elevator is definitely accelerating upwards. And if we do net force equals ma, you've got 850 up minus 735 down equals 75 times acceleration. Subtract and divide, and you get 1.5 meters per second squared. Number 3. The 4 kilogram block is accelerating across a frictionless horizontal table at 1.5 meters per second squared. We want to find the mass of our object M1. So this is an Atwood problem. Nice thing is there's no friction. So if you consider the two objects, M1 and 2, moving as one system, then if you draw the force diagram for both, you can kind of just combine their forces together and ignore the tensions in the ropes. So for M1, you've got M1G pulling down and tension pulling up. For M2, you've got force of gravity, and normal force, which aren't doing anything to do with the M2 moving left or right, so we can ignore them. But we've got a force of tension in the rope. These two tension forces are the exact same, and we can ignore them. So that means when we're doing our net force equation, we can just look at the forces, or force, that is in the direction that this thing is moving, right? So positive direction is over the pulley and down. So we really just have M1G pulling down in that direction and nothing opposing it. So M1G is our net force on the system. You still have to combine their masses though, so you still have M1 plus M2 times A. Now we know M2, we just don't know M1, so you still have M1 times 9.8 equals M1 plus 4 times 1.5. You distribute the 1.5, combine like terms, and M1 is 0.72 kilograms. Skipping the algebra. Number 4. If the horizontal surface is frictionless again, what's the acceleration of the system? This one looks more complicated than it is. This 7 kilogram block, while it has several forces acting on it, it's got tensions in both directions. Neither of those tensions are going to really matter, right? We're gonna draw a force diagram for all three objects. So normal force, force of gravity. You got tension 1 here. You got tension 2 here. The 5 kilogram block, you got 5 times 9.8, or 5G. Going down, you got T1 going up. So T1 and T1 essentially cancel each other out in terms of looking at this as a system. The 1 kilogram mass, you got 1 times G, or just G, going down, and you got T2 going up. So these two T's and these two T's, when you look at it from a system standpoint, negate each other. So when you look at net force equals mass times acceleration, the net force on this system causing it to accelerate clockwise, you've got 5G pulling clockwise, you've got G pulling counterclockwise, and that equals the total mass, 1 plus 7 plus 5 times A. If there was friction, we would have to take that into account for the 7 kilogram block and subtract 7 times 9.8 times mu, but there is no friction in this case. So we just have left with 4G equals 13A. So 4 times 9.8 divided by 13 is 3. Number 5, a net force F acts on an object of mass m, causing it to accelerate at 4 meters per second squared. If the same force acts on an object with a mass of 2m, its acceleration will be, so if you look at net force equals ma, we're essentially keeping the net force the same. And we're saying with mass m, you get an acceleration of 4. And then if you change to have 2m, so you're making the mass twice as big, what you're essentially doing is making the acceleration half as big. It's an inverse relationship between mass and acceleration. So if mass doubles, acceleration gets cut in half, assuming the net force stays the same. So if our acceleration was 4 and now it's getting cut in half, it's going to be 2. Number 6, coefficient of friction between the basket of apples and the ground. So force diagram for the basket, you got force of gravity down, which would be 25 times 9.8. Normal force up, same thing. You got 120 Newton force to the right that's being applied. And there's going to be some friction to the left. And it tells you that the acceleration of the basket's 1.8. So net force equals mass times acceleration. You got 25 times 1.8 on the right. You got 120 to the right minus your force of friction, which is mu times mg. So 120 minus mu times 25 times 9.8 equals 25 times 1.8. The only thing we don't have here is mu. Do the algebra, and mu is 0.306. Next problem, a student drags a 7 kilogram box across the floor by exerting 45 Newton force, and we want to know the acceleration. So, free body diagram, we've got force of gravity down, you've got friction to the left, kinetic. Normal force is not going to be the same as the force of gravity because we're applying a force that's lifting up a little bit, so normal force is smaller. And we've got this applied force of 45 newtons. We can use sine and cosine to get our components of this 45 newton pull or push. The y component is 18.3 newtons. The x component is 41.1. And when we do F net equals ma, the net force is going to be along the plane that we're moving, 41.1 to the right minus mu times our normal force, that's force of friction, equals ma. Now we need to figure out that normal force, and it's going to be normal force plus 18.3 equals the force of gravity going down. The two up forces balance the force going down. So our force of gravity down is 68.6. So if you subtract 18.3 from that, you get a normal force of 50.3. So we've got 41.1 minus mu, which is 0.52, multiplied by the normal force, equals 7a. The only thing we don't have is a, and it's 2.13. Number 8, a 72 kilogram skydiver drops from a helicopter and is accelerating downward at 8.6 meters per second squared. Find the drag force acting on her. So since her acceleration is not 9.8, you know there has to be some drag force. And by drag, I just mean friction with the air. So quick diagram, she's got force of gravity down, she's got a little bit of drag going up. We're trying to figure out what that force is. So F net equals ma. Net force would be this drag force up minus mg. Mg for the skydiver is 705.6 equals her mass, 72, times a, which is 8.6 in the downward direction. She's accelerating downward, so that's negative 8.6. Solve for this drag force, and it's 86.4 newtons.